All right, everyone, welcome back. And we're going to start shortly. All right, I hope all of you are doing well. And just confirm the audio quality here. All right. And good morning to you all. Really. All right. All right. So I think we can start now, right? All right. So again, during the class, if you have any query, feel free to ask in the live chat. I'll be definitely answering your queries. With that said, let's start our discussion on this subject. So this is your first class on control system engineering theory specifically. And sometimes this subject is considered a branch to be a branch of mathematics instead of being a branch of engineering, right? This is a subject which is taught to electrical engineers, electronics engineers, mechanical engineers as well. This is one of the multidisciplinary subjects where the knowledge you gain from this subject actually comes from many different disciplines. Okay, so there are some parts from mechanical engineering, there are some parts from electrical and electronics engineering in this particular course, right? And this is designed in such, and this is not because we designed a curriculum in a particular way. This is simply because this subject, the nature of this subject often creates a this subject deals with making a mathematical model for a system which we want to automatically control, right? So this subject is often known as automatic control systems, right? So we shall be talking about automatic control system, how we can actually automate things mostly, and how to mathematically describe systems. We shall learn all those things. But before that, I should explain that this subject originated, I mean, the formal rigor of this subject originated back in 1940s. And back in those days, try to imagine, so we are, imagine you yourself to be an engineer working in 1940s, right? You did not have a computer, you did not have a calculator, right? So if you wanted to calculate a big expression, you would do that by hand, right? So back in those days, the whole objective of this subject was to be able to describe the mathematical properties of a certain system, okay, in a way that can be handled without a calculator or a computer, right? Do you understand my point? So we are talking about a time where calculators, computers did not exist, right? So back in those days, people invented methodologies which could be used. Hold on, let me just reduce the volume. Yeah, back in those days, people developed methodologies which could be used to analyze the properties of a system, to figure out how to be able to automatically control a certain system without actually using heavy computational tools. But nowadays the landscape has changed drastically, right? Nowadays we have computers, we have calculators, we have all these things, right? So even if I give you a quadratic equation, you can just put it into your calculator and you can solve it. But back in those days, doing anything required manual work, right? So solving a quadratic equation was easy, but solving a cubic equation wasn't that much easy, right? So understandably, people did everything manually, right? And back in those days, the whole objective was to simplify things. And that is what we are going to learn here. Mostly, funny thing is that whatever we're going to learn in this subject was developed back in 1940s, 1950s and 1960s. We are not really going to learn anything modern about it, okay? The modern parts of this subject are beyond our undergraduate curriculum. In fact, it is beyond the modern parts of the control system engineering is beyond any undergraduate curriculum for that matter, right? So we are going to learn, what we are going to learn is literally ancient history in terms of technology. But understandably, understanding this ancient history of technology actually enables you to understand the modern aspects of this subject. So we shall touch a few modern aspects of this subject at a later point, but we shall begin by learning how people dealt with automated control mechanisms back in 1940s, 1950s and 1960s, right? All right. So with that knowledge, let's figure out something very simple, right? Let me tell you about a very simple thing. Imagine, okay, right, if I ask you this question, how many of you have, so for example, how many of you have driven a car, for example? Maybe a motorcycle would be also nice, okay? Maybe a bicycle is fine also, right? How many of you have driven a vehicle? Any kind of vehicle, right? I believe almost all of you, right? Okay, a bicycle would do, a motorcycle would do, a four-wheeler would do, a truck might also do. If you have driven a vehicle, you know you cannot drive a vehicle with your eyes closed, right? Question, the thing is, you cannot drive your vehicle with your eyes closed. Let me say, okay, you people are familiar with this kind of boxes, right? We electrical engineers, we draw this kind of boxes. And then we tell you that, okay, this is representative of a system, right? We are pretty funny people in that regard, right? So I have just drawn a box, right? And I'm telling you, maybe this is a vehicle, right? This is a vehicle, say this is a vehicle, right? So you're driving a vehicle. Question is, can you drive it with your eyes closed? Can you drive a vehicle with your eyes closed? Of course, no, you cannot drive your vehicle with your eyes closed, right? Why? The answer is pretty simple. You cannot see anything if you keep your eyes closed, right? Question, why do you need to see things, right? Answer is, you need to see things to make adjustments, right? You need to see things to make adjustments to the speed and control the vehicle, right? Unless you see things, you won't be able to know what to do, right? You won't be able to control the vehicle, right? The term control is coming up here, right? Understood? But imagine an ideal world. Imagine an ideal world where everything is so ideal and so perfect that you have, what should I say? You have a mechanism in which, for example, imagine you have an ideal vehicle, right? In which if you press on the accelerator pedal, okay, for a certain amount, and your speed will become a certain amount, right? So for example, you press the accelerator pedal with a certain pressure and your speed is now 60 km per hour, right? Something like that. you are driving on a straight road. Imagine you are driving on a straight road at a constant speed of 60 km per hour. You are keeping the accelerator pedal pressed at a constant pressure. So the vehicle is basically going at a constant speed, for example. Imagine something like that. But question, so you're driving on a straight road, everything is perfect, right? Question, can you still consider that you can drive with your eyes closed? The answer is now yes, sort of. Why? Because if you're driving in a straight road, you are not making any adjustment to where you are going, so you don't have to steer your vehicle, for example. And when I say everything is ideal, then all the other vehicles are also running at the same speed. So if all the other vehicles on the same street are running at the same speed, so there is no question of any collision happening, right? So you're driving on a straight road on a vehicle at a constant speed where everything is perfect, and so perfect that all other vehicles are running at that same constant speed, right? So you don't have to steer your vehicle, neither do you have to control the speed of your vehicle, right? Neither are you controlling the orientation of your vehicle, where it is going, so you're not steering your vehicle, or nor are you controlling the speed of the vehicle, because you don't need to. Everything is so ideal, there is no point of any no collision is going to happen, no problem is going to occur. Under this kind of ideal situation, you can drive blindly, right? Without looking at anything, you can drive, right? Do you agree? Do you understand what I'm saying here? If everything was so ideal, then you could have driven without looking at it, right? Right? There won't be any collision because every other vehicle is traveling also at the same speed of yours, right? So that way, everything is so ideal, you don't need to control it, right? Right? So do you agree with my point? So this is again going to be a gentle introduction to the subject. Why you need this subject. That understanding is actually pretty important in my opinion. Just blindly jumping into the mathematics of this subject, and I assure you there is a huge amount of mathematics related to the subject. But before we jump into the mathematics of the subject, okay, I shall try my best to lightly introduce the subject to you. It's going to be a gentle introduction to the subject. In any case, do you agree to my point? Agree with my point? And also, please try to interact in the live chat, so I actually get to see that you understand things, right? You will learn shortly why I ask you to interact. Yeah, I did not ask you about the mathematics. Yes, apart from Laplace transform, we shall have quite a few other mathematical tools, right? Right? So my point was, if you are driving your vehicle in an ideal world where everything is ideal, where you press the accelerator pedal a certain amount, your vehicle would run at a certain speed, say 60 km per hour, and you are driving on a straight road where all the other vehicles are also traveling at the same speed, right? So there won't be any collision, you don't need to steer your vehicle, so you can drive your vehicle blindly. That's true, right? That's true. But the problem is, nothing in this world is ideal, right? Nothing in this world is ideal, right? Understandable, right? Is that understandable, right? So there might be, so even if your vehicle is ideal, so imagine an ideal situation again. Now imagine your vehicle is perfect, right? So it is going to travel at 60 km per hour. But consider an Indian road, and where you have gaddas all over, right? So you have ditches, right? For example, there are some breakage in the, imagine there are some potholes in the road itself, right? And one of your wheels actually falls into one of the potholes. So even if your vehicle wanted to maintain that 60 km per hour speed, now it won't be able to, simply because an external disturbance came in. In an ideal world, there are no disturbances, everything works perfectly, but nothing is ideal really, right? Nothing is really ideal. So the road might have potholes, something like that, and there your vehicle would have a reduced speed. Not only that, there might be some problem with the steering, right? You might have to steer it back to the lane, right? Because that external disturbance, namely a pothole in the road, could cause a steering problem, right? Could cause a steering issue. So it could steer the vehicle out of lane, right? That could happen. Understandable? Now, the moment that happens, try to understand something. Before this, in the ideal world, we assume that there won't be any collision happening, simply because all the vehicles were traveling at the same speed. Now, since your vehicle is no longer traveling at that same speed because you simply fell into a pothole, right? The fate of all other vehicles traveling on the road are now determined by what you are doing, right? So somehow if you stop, then what happens? A huge collision is going to take place because everyone on the same road is traveling blindly, right? Because everyone is thinking that everything is ideal apart from the pothole that you fell into, right? And if you somehow stop, then all other vehicles are going to collide behind your back. That's going to happen simply because everything is traveling at the speed of 60 km/h and the drivers are not looking, right? Because they are assuming everything to be ideal. Try to understand what I'm trying to say here, right? So a small disturbance that happened to you actually not only determines your fate but also the fates of other people on the same road, right? Again, keep in your mind the term disturbance. All right. All right. So I believe you understand this this terminology, right? All right. So now that happened, something like that happened, right? So you understand, even in a perfect world, even if there are small disturbances, even if there are small chances that things could go wrong, things will go wrong. Okay, in philosophy it's called Murphy's Law. Murphy's Law says anything that can go wrong will go wrong. Okay, and keep that in mind. This is a philosophical proverb here. Anything that can go wrong will go wrong. So in an ideal world, even if something goes wrong, something very small goes wrong, it might have catastrophic effects, right? So ideal situation. So for example, your vehicle should have a mechanism. So if you want to drive your vehicle blindly still, then your vehicle should have a mechanism to be able to avoid those kind of, or rather correct itself after falling into a pothole, right? So if the road is not perfect, in that case your vehicle, if you want to drive it blindly, your vehicle should have a mechanism to correct itself both in terms of speed and in terms of orientation. Then you can once again drive blindly. All right. Then I am assuming all the vehicles are also perfect. Now, so for example, you are traveling on the same road again. The engines of one of the vehicles are failing, right? So it is no longer being able to keep up the speed. What's going to happen then? Then the fates of not only that vehicle but also the other vehicles will now be at stake. This is again quite understandable what I'm trying to convince you here of. Right? The simple idea is that nothing is ideal in this world. Okay? Even if you imagine an ideal world, there would always be disturbances. So this vehicle is not traveling in a perfect world. It is always encountering what we call, rather let me use a different ink. So it is always encountering what we call a disturbance. And it shall always encounter this no matter what. You can never create a perfect world. And since you can never create a perfect world, there shall always be certain disturbances, right? So this vehicle is always encountering certain disturbances, right? And try to understand, because there are disturbances, you need to have a driver driving a vehicle. Is that understood? This simple terminology here. Question is, why do I even need a driver to drive a vehicle? Because nothing is ideal, right? Even if I have a straight road, completely flat, okay, absolutely without any issue, all the vehicles are supposed to run at the same speed. Even after that, you cannot let a vehicle go without a driver, simply because there might be unforeseen disturbances, right? There might be unforeseen disturbances. So the objective of the driver is to drive the vehicle. So driver is driving the vehicle. Why is the driver driving the vehicle? Because nothing is ideal. That's the point here. The driver did not need to drive the vehicle if there were no disturbances, right? If everything was ideal, you won't even have to drive the vehicle, right? You can just set the vehicle at a constant speed and it will reach its destination absolutely without any issue. But since there are disturbances, you need to have a driver. Is that understood? You need to have a driver. It's very simple, as simple as that. All right, you need to have a driver, right? In control system terminology, this is called a system and this is called a controller. A controller is something that is controlling a system. This is a system and this is a controller. Okay, now my question is, why does the controller exist? Why does the controller exist? That's my question. Why does the controller exist? Okay, someone is asking, in case of railways, they follow a particular path. So can't it be possible to drive it without a driver? No, unfortunately, no. Even if you are able to control it remotely, no. Because you might, the way you stop and start the vehicle, okay, requires human intervention. There also, you are traveling, you are, what should I say, starting and stopping the vehicle precisely, right? And for those kind of things, there might be some disturbances that could be unforeseen, right? And for that, at least to start and stop the vehicle, you need manual operation, okay, right? And when the vehicle actually enters a big station, there also you need human intervention. But perceivably, I can say that railways can be controlled automatically to some extent. Okay, if you can assume that everything is perfect, then yes. Elon Musk is making Hyperloop in the US, and that would probably run automatically, right? Because all the unforeseen disturbances are being kind of eliminated. Yes, that's the point. You can have unforeseen disturbances, right? Right. You can assist the driver by using some kind of automated driving technology, right? All the automated driving technologies, all right, self-driving technology, they require the presence of a driver. Even though they can self-drive for the most part, but still those would require the presence of a human driver. But again, the point remains, okay, you are saying automated driving or self-driving. It means the human part of the driver is being turned into a machine, right? Instead of a human entirely controlling the vehicle, a computer is probably controlling the vehicle. But something is controlling the vehicle. That's the point here. Okay, it doesn't need to be a human. This driver, what I'm saying here, does not always need to be a human, right? It could be a robot, right? It could be a computer, right? All right. It could be something, but it should be there, right? You cannot drive a vehicle without a driver. The driver could be a human, could be a robot, could be a computer, could be anything, right? All right. It could be a combination of a computer and a human, right? Like in self-driving cars. In self-driving cars, you need to have a driver, but the car for the most part can drive itself, simply because it has a computer as a driver. Okay, you need to be able to control it no matter what. Okay, even if you have autopilot that actually controls things. Yes, all the autopilots actually requires certain amount of artificial intelligence, and they have vision sensors, all those sensors, right? All the human perceptions are built in as a computer, right? So yes, you need to have a driver. Okay, a human driver or a machine driver, no matter what. So that's the controller, right? My question is now to you, why do I need the controller? Why does the controller need to exist? A very simple question. Why does the controller need to exist in this scenario? And the answer would be pretty obvious. Because nothing is ideal. The controller exists because nothing is ideal. Because of the disturbance here. Right? Try to understand the terminology here. You need to have a controller simply because you have unforeseen disturbances, or rather foreseen disturbances in the system itself, right? Is that understood? All right, so since you have disturbances, you have a controller, yes, to overcome non-ideal situation. So if imagine you are living in an ideal world where there is no disturbance, if there is no disturbance, absolutely zero disturbance, then you won't need a controller, right? So disturbance is the reason why reason for the existence of controllers, right? Understandable? So there is a popular French term for this. It's called raison d'être, reason for existence, right? So controllers' reason for existence is the disturbance. Controllers exist because disturbances exist, right? Yes, absolutely. So controllers raison d'être is disturbance. All right. So that's understood, I believe, right? All right. So with that said, again, so I'm trying to clear up the terminology here so that actually you have some understanding of what is happening here, or why we need things as they are designed particularly here. All right. All right. All right. All right. So all right. So now a driver is driving the vehicle, right? But see, this kind of block diagram, so this is called a block diagram, right? So we are actually showing you the interaction. So driver is somehow sending some input to the vehicle, right? But in order for the driver to be able to send some input to the vehicle, in order to control it, the driver needs to have some input for themselves, right? Right? So right now what I have drawn is a blind driver, a driver who is not seeing anything. Try to understand, because the driver himself is not getting any input, right? The driver himself is not getting any, or himself or herself, okay, or maybe itself, okay. The driver is not getting any input, okay. But without getting any input themselves, the driver cannot drive the vehicle, right? This is the signal the driver is generating, okay. All these lines are representing signals, right? And you studied signals and systems, right? So this is a signal being generated by the driver, and this signal actually controls the vehicle, okay. What kind of signals does would the driver produce? For example, the driver would produce a signal that would either depress or release the accelerator pedal, right? So the driver would either press on or release the accelerator pedal, so accordingly the acceleration will change. Or maybe the driver will press on the clutch, maybe not, right? Press on the brake, right? And also driver will steer. All these are signals that are actually coming from the driver. Now for our purpose, we're drawing a single line, okay, representing a single signal coming from the driver to the vehicle. But in reality, there will be like 4 or 5 signals coming from the driver to the vehicle, right? Controlling the clutch, controlling the accelerator, controlling the brakes, controlling the steering mechanism, okay, changing the gears, everything. All these kind of signals are going to come from the driver to the vehicle. But for the simplicity's sake, we're just drawing a single line. All right? Right. So if that is fine, try to understand that the driver cannot, what should I say? The driver cannot control the vehicle unless the driver sees what is happening, right? Unless the driver, why would the driver accelerate? Because everyone right in front of him is accelerating, or maybe he or she has a empty road right ahead of him, right? So under those scenarios, the driver would accelerate, right? If something comes up or if there is a red light, of course, the driver would release the accelerator pedal and hit the brakes, right? Constantly the driver would be steering, but based on what? Based on what he sees, right? Based on what he sees. So he would need to see things, right? He would need to perceive how fast the vehicle is moving, where the vehicle is going. He should be able to see that, okay? Understandable. The driver needs to be able to see all those things, right? Understandable? So driver need to be able to figure out what the vehicle is doing, right? Because this is very simple. When you are hitting the accelerator pedal, you are asking the vehicle to go faster. But the point is, whether or not the vehicle would go faster, it depends on the vehicle, right? So if you are sitting on a broken vehicle, okay, broken vehicle which does not run, and you press on the accelerator pedal, you cannot expect the vehicle to go faster, right? Very good point. The controller itself acts as a system. Every single block that I represent here are systems themselves, and they would probably have subsystems inside those. So the vehicle itself has many subsystems and many internal controllers built in within that, right? So we are looking at a top level abstraction here, okay? The vehicle can be also subdivided into small subsections, okay, subsystems rather, right? So we're looking at a top level abstraction. So we are just keeping our abstraction as simple as possible, particularly. Yes, but every single block here is a system, all right? We human beings are systems. Many controlling mechanisms are happening within us, right? Understandable, right? So as I was saying, the driver needs to be able to see everything, right? And for that matter, so say when the driver is driving the vehicle, okay, so try to understand again, once again, just the way I was saying. So for example, if I press on the accelerator pedal, all I am doing is I am asking, let me again reduce the volume, something is wrong with this. Okay, if I am pressing the accelerator pedal, all I am doing, I am asking the vehicle to go faster, right? Right? But just by pressing on the accelerator pedal, I cannot ensure that the vehicle goes faster. I need to be able to see and verify that. I need to be able to see and verify that, right? If I hit on the brakes and release the accelerator, okay, I need to be able to see that the vehicle actually stopped or the speed got reduced, right? I cannot just blindly press the accelerator and expect the vehicle to go faster, right? I cannot just press the brake and expect the vehicle to go slower, because it will go slower probably if the vehicle is fine, but how much slower I cannot figure out unless I see it, right? So if I don't see it, then this kind of mechanism is known as a feed-forward control. In feed-forward control, we assume things to be ideal, and under ideal scenarios, okay, we would kind of know, but by pressing this much on the accelerator, I would increase the speed by this much, something like that. But nothing is ideal, and since nothing is ideal, we need to be able to see things, and that is done through something called a feedback. Okay, so the name of this subject is also feedback control systems. Okay, so this was feed forward. Now we have a feedback, and now feedback of what? Feedback of what? Feedback of how fast the vehicle is moving, how fast the vehicle is accelerating, or how fast the vehicle is decelerating, or the direction in which it is moving probably. So these are all the outputs of the vehicle, right? Again, I'm drawing a single line just to keep things simple, but these are all the outputs of the vehicle, right? And I need to be able to see the outputs of the vehicle. Rather, the driver needs to be able to see the outputs of the vehicle. Okay, is that understood? And of course, in order to see that, how fast exactly is the vehicle traveling, vehicle moving forward, okay, what is the acceleration, you have a huge set of control panel in every vehicle, right, where you can see everything that is happening to your car. Also, you have your eyes, so you are looking at your road, so that you are also looking at your environment. So taking all this together, you can imagine this entire system that gives you perception of your environment, as well as how fast or how slowly your vehicle is moving, where your vehicle is going, is a set of sensors. Now this set of sensors would include your eyes as well, would include your ears as well, right? If someone is honking right behind you, you need to be able to hear that, right? Okay, understandable? So something like that. If there is a vehicle standing right in front of you, okay, or if a person comes right in front of you, you need to be able to see that, right? So these sensors include your eyes, your ears as well, right? Your sensory perceptions as well. Also, all the meters and everything that would come with the vehicle as well. So you have a set of sensors, and from that, what you are perceiving about the environment and the vehicle itself, how well the vehicle is behaving, right? Where it is going, whether or not it is whether or not it is obeying your command, for example, whether or not you are doing it right. So these sensory perceptions will give you an idea of that, and that is what you need as the driver, right? As the driver. So this is something you need as the driver, but there is a problem, small problem. All right, so the driver needs to be able to see what is happening, right? That's again understood, right? Is that understood? That's understood. Pretty simple, right? All right. So with that said, the problem is that here we do not really have a mathematical way of representing the mindset of the driver. Imagine this entire single line is representing the speed of the vehicle, right? Representing the speed of the vehicle, right? So imagine the driver wants to run the vehicle at a speed of 60 km/h, and accordingly the driver would press harder on the accelerator, say, right? And the vehicle is accelerating, so it means the speed of the vehicle is increasing. The driver needs to keep track of the speed, and if the speed exceeds beyond 60 km/h, then the driver need to release the accelerator pedal accordingly, so that the speed actually reduces. And if the speed again falls behind 60 km/h, then the driver would again slightly press on the accelerator pedal, right? So this kind of adjustment is possible only if the driver or the controller is comparing the output with a certain reference, right? This kind of adjustments are possible only if the controller is comparing the output of the vehicle or the system in this regard with a set of prefixed values or with a set of reference, right? So I want the vehicle to travel at this speed. Let's see how fast I am going. Let's see, currently I want the vehicle to travel at the speed of 60 km/h, say, and right now the vehicle is traveling at 40 km/h. Understandably, I need to press harder on the accelerator pedal, But who would tell that to the driver? The difference between what I want and what I have will tell me that, right? What I want is my vehicle to run at 60 kilometers per hour. But what I currently have is the vehicle running at 40 kilometers per hour, right? So the driver needs to press harder on the accelerator pedal. But how would I know that? I would know that, I as the driver would know that by simply comparing the reference value with the output. So we have a special block diagram symbol here. Okay, and this symbol is a very special symbol. It simply represents that what we are reading here, what we have here, whatever we are reading from here, we are subtracting with the reference. So this is the reference value, and we are subtracting the output from the reference value. So this is plus and this is minus. That is the indicative here, right? So we are subtracting them accordingly, right? So here apparently we would have the knowledge that my vehicle is running 20 kilometers per hour slower than how fast I want it to go, right? So accordingly I will press harder on the accelerator pedal. Rather, the driver would press harder on the accelerator pedal. I think this is understood, right? If not so, if say for example this is instead 80 kilometers per hour, but I want to go at 60 kilometers per hour, then the difference would tell me that okay, we have a negative change required, right? We need to reduce the speed. This difference here, if I measure the difference or compare the difference, and this block is literally known as a comparator, right? It compares. This comparator would tell the controller or the driver that okay, I need to reduce the speed. Maybe I need to release my leg from the release the accelerator and slightly press on the clutch and the brake. Maybe, I don't know. Okay, at least I have to reduce my pressure on the accelerator. So that's understandable, right? So with that knowledge, I think this is quite understood that this comparison needs to be done. And again, for the driver, this comparison is happening inside the driver's head, right? The driver is looking at the sensors, looking at how fast he is moving, and accordingly he also knows how fast he needs to go, right? And accordingly he compares, he does this comparison inside his head. So this is a comparator, right? And this is a very simple block diagram of a control system. This is a very simple block diagram of a control system, right? All right. So let me now copy this diagram to a more generic one, to create a more generic one. Okay. So again, before I just move forward, feel free to ask any question that you might have. Before I move forward, feel free to ask any question that you might have. All right. Feel free to ask any question that you might have. I'll be back in like 2 minutes. All right. All right. So let's proceed, right? I don't think you have any queries. All right. Fine. All right. So the system we are controlling, let me just zoom in a bit. All right. Oh. The system we are controlling, we call that a controlled system. So let me just introduce to you the terminologies we actually have. All right. So this is the controlled system, right? Right. All right. So the transfer function for the again, I shall introduce to you the term transfer function, but the mathematical description of the system, for that matter, let's represent that with say, I don't know, say G2 maybe. All right. So this is the mathematical description. This could be a transfer function model. This could be a state space model. This could be any other type of model. Okay. But this is a mathematical description as far as we people are concerned. Okay. So the controlled system is a system that is being controlled by a controller, right? For our previous example, this was our vehicle, right? So we have a controlled system. So understandable, right? That's understandable, right? Then what we have is that we have a controller, right? Now instead of calling it a controller, I shall call it control elements, because a controller itself actually has several other components as well. We shall learn all those things later on, but we shall call it control elements. Right. And let's call the mathematical representation of this to be say, I don't know, G1 maybe. Okay. All right. And from that, this set of control elements is actually sending a signal to the controlled system so that it can actually control the controlled system. Is that understood? Right. So this signal is being sent from the control elements to the controlled system, and understandably they behave accordingly, right? So this is the human driver in this particular scenario and the vehicle. Then you have a mechanism for finding the output of the controlled system. So let me just again draw the output of the controlled system. So this is the output of the controlled system, for example, and this output of the control system is being read by a set of sensors, right? Set of sensors, something like that. So those set of sensors are going to be called I shall call them feedback elements. Usually they contain sensors, right? So these are the feedback elements, right? These feedback elements would receive signals from the controlled system, right? So basically what the controlled system outputs is received by the feedback elements, and that is being fed back to the control elements, and it's the responsibility of that part to compare what we get from the feedback elements and what we want. So we have something called a reference input. So this is the reference input, and this reference input is being compared with the, let me just hold on. All right, so this is the reference input, and this would be compared with what we get from the feedback. Just like our previous example, we have a plus, we have a minus here, okay, and all right, so this is basically a comparison happening. All right, and this comparison, okay, what we get after the comparison, so this is the reference and this is what we have, right, from the output of the control system. So this actually goes into the control elements. All right, up to this part I think is understood by you, right? Now often what happens is that we do not really have a reference input as such, right? So try to understand. Again, think about the human driver here. Okay, for the human driver, for our example, the reference input was a certain amount of speed at which you wanted to move. Let me hold on this for a second. Yeah, it's working. All right, so the reference input was a certain amount of speed, right? But what happened? Try to understand that in your mind you have an idea about speed, right? Okay, and that is being somehow translated by your brain into a certain comparison with what you get from the feedback elements, right? So how fast you want to move is an abstract idea in your brain, right? How fast you want to move is an abstract idea in your brain, and that abstract idea needs to be materialized into certain numerical value, right? So what you essentially have, instead of this reference input, we call this the reference input. Instead of this reference input, what you actually have is a set of commands that are in your head, okay? So the command would be something like go faster, or maybe go slower, something like that. This kind of commands is something you have in your mind, right? And from there you are generating the reference inputs. So this is the reference input, and you are generating the reference input by means of having some command inside your head. The command could be go faster or go slower, something like that. So let's write down the names now. For example, this is called the command signal. Okay, command signal, and a command signal is represented with V. Okay, it's a good example for our purpose because we are considering the velocity or the speed to be our command signal, right? Right. And this block here is a system. It's called the reference input conditioning elements, or rather reference input conditioning. It's called the reference input conditioning elements, set of reference input conditioning elements. What signal this one generates is the reference input. So this is the signal we call the reference input, and reference input is represented, okay, let's call everything with capital names. So this V, and reference input is called R. Okay, the reference input itself is called R. Okay, of course this is called the output of the system, right? It's called the controlled system's output, but in our control system nomenclature this is called the controlled variable. The name is controlled variable. The output of the controlled system, for our example it was the vehicle, the output of the vehicle would be called the controlled variable, or controlled variables for that matter. So this output is actually the controlled variable. So this is the controlled variable, right? So the output of the system, right? So this controlled variable has a name. Once again, we usually call this a C. Represent that with a C, right? So this controlled variable is again the output of the controlled system. This is being received by the feedback elements. Now feedback elements would have a transfer function or some sort of a mathematical model, could be a state space mathematical model or something like that. We call its transfer function or its mathematical description to be H. So this is again standard nomenclature, right? And the output that we receive from the feedback elements, and again feedback elements would include your eyes, your ears, the entire display panel of your vehicle, everything. Okay, we call that the feedback signal. So right, so this is the control variable, and after going into this, what we have is the feedback signal. So this signal is the feedback signal. Okay, and the feedback signal is called a capital B. Okay, understandable, right? I think it's understandable, right? So this comparator, so this is a comparator. This comparator is comparing the reference input with the feedback signal, right? So comparing means just subtract them, right? So that gives you the difference. How much you are yet to go, or how much you have to release. So this is basically a subtraction, simple subtraction. Comparison means subtraction in this particular scenario. So this difference between the reference input and the feedback signal is called the actuating signal. So this signal what we have here out of the comparator here is called the actuating signal, right? This signal in particular that it appears here is called the actuating signal. This signal that appears here is known as the actuating signal, and it has a symbol of E, right? Understandable? Now it has a better name, and that is why we have this E representing this signal. Okay, this shows you how much you still have to go or how much you have to reduce in terms of your reference input and the control variable, right? So what is the difference between what you have and what you want? That difference is known as the error signal. Often this is called an error signal. So I would rather, instead of calling this the actuating signal, I would rather call it the actuating error signal. Actuating error signal. And since this is the error signal, we have a name E. Okay. So the actuating error signal is the difference between the reference input and the feedback that we receive from the feedback elements, right? And that actually goes into the control elements. So namely the driver himself or herself, right? Now based on whether I have to go faster or whether I have to go slower, so this will basically tell me the difference between how fast I want to go and how fast the vehicle is currently moving from our particular example. And accordingly, this will decide the control element, or namely the driver will decide whether the driver needs to press harder on the accelerator or release the accelerator, right? So the driver receives a signal, and that signal is the difference between the speed at which the driver wants to travel and he is currently traveling at. The difference between his current speed and the speed he wants to travel at, right? And based on that, he will decide what to do with the accelerator, whether to press on it or to release it, right? So this is the output of the controller, okay? A pressure on the accelerator. So what output we get out of the controller is represented with a capital M, and it is called the manipulated variable. Okay, all right. So this is called the manipulated variable simply because the controller is actually manipulating the error signal and feeding it in a way that is understandable by the controlled system, right? And of course, the output of the control system is the controlled variable. But always keep in mind that none of these would be there if there wasn't any disturbance, right? So the disturbance is all those non-idealness in the scenario, right? Everything that is non-ideal, okay, from the perspective of the control system can be considered to be a disturbance. So for my particular scenario, I am saying so this is disturbance, and the disturbance comes externally again into the system I am controlling. So this is a very important point to note. Again, all these control elements, feedback mechanism do need to exist simply because there is a disturbance, right? Nothing is ideal in nature, right? So the disturbance is actually feeding into the control system. We call that with a capital D. But along with that, there is something else. You might have heard these terms, disturbance and noise, right? Disturbances and noise, right? Often what happens is that, and this is again the fault of the teachers mostly. Often many teachers would teach you that disturbance and noise are the same thing, and you would have this kind of wrong idea. But the point is, disturbance and noise, these two terms, even though they have kind of similar meaning in the English literature, okay, they do have completely different meaning in engineering, okay? They do have completely different meaning in engineering. Disturbances are those non-ideal situations that affect the controlled system. But noise is what we get in the measurement system. So if I say noise, okay, noise is what we get into the measurement system. Again, what am I saying? Which one am I calling to be the measurement system? The measurement system is the feedback mechanism, right? All the sensors are measuring how fast the vehicle is moving, which way the vehicle is moving. All these things that are being measured are coming from the measurement mechanism or the measurement system, right? Namely the feedback system. So the feedback system is the measurement system, and the noise actually comes into the measurement system. And the noise is represented with capital N. Alright? So although the terms, English terms disturbance and noise, they do appear to have the same meaning, they are two completely different things as far as we engineers are concerned. Disturbances are those non-idealness, okay, that affect the control system. In an ideal world, you would not have disturbances whatsoever, okay? But in an ideal world, you also won't have noise, simply because in an ideal world, you would not need these feedback elements. Do you understand what I'm saying? If there was no disturbance, there would be no noise, simply because if there was no disturbance, I would not need to measure anything. Everything would be so perfect that I would not need to measure anything, so there won't be any noise either. Okay, not because there wasn't any noise, but because we do not need to measure anything in the ideal world, right? But since nothing is ideal, there are non-idealness in the environment, in the system itself, okay? There are non-idealness, those things are modeled as disturbances, all right? And because we have disturbances, we need to have a feedback mechanism. We need to be able to measure things, and accordingly we need to take care of the differences. Accordingly we need to take care of the actuating error signals, right? And because of that, we need to measure things, and because we are measuring things, there might be some measurement noise, okay, right? So this is called noise. So this is the difference between disturbance and noise. Again, let me repeat, disturbances are those non-idealness, okay, in the system and in the environment that would affect the controlled system. and noise is associated with the measurement or the measuring equipments, the sensors. Okay, okay, those noises are random fluctuations in the signal that we measure or the measuring equipments. All those random fluctuations are modeled as noise that are associated with the sensors or measuring elements. Okay, I think I cleared up the difference between a disturbance and noise. All right, so I think this much is fine, I think. Okay, all right. Again, if you have any query, feel free to ask right now. Okay, all right. So now try to understand. And again, the same vehicle terminology, right? If you drive a four-wheeler backwards, what happens? Automatically certain lights will glow. Okay, if you hit the brakes, certain lights will glow. But do you have to manually make them glow? My point is no, right? Right? So if you are hitting the brake, automatically the red lights behind your vehicle automatically will glow. To indicate the vehicles that are trailing you, the vehicles would know that you have pressed your brake. So that those kind of systems are automatically controlled based on what you are doing. I mean, you are not directly controlling those lights, right? Those brake lights, okay? Those kind of things you are not directly controlling, right? Those kind of equipments are being indirectly controlled based on what your vehicle is currently doing, right? Right? If your vehicle is backing up, it will play a certain melody, something like that. This kind of things are happening, right? But those things are automatically triggered, okay, based on what your vehicle is doing. So this kind of terminology is known as an indirectly controlled system. So this is called an indirectly controlled system. Now, based on the control variable, these indirectly controlled systems are controlled. Okay? You do not directly control them based on what your vehicle is currently doing. This kind of indirectly controlled systems are controlled. Sorry, it should be in this color, right? Because this is a system. Just keep in mind, all the systems are being represented by yellow, and all the other colors are being used for the signals. And again, this is a sequel to signals and systems, right? So our ideas that we gathered during our signals and systems classes will be directly applicable here. And again, when the lights are turned on and all those things, okay, we get to see their outputs, okay, and those outputs that we get from the indirectly controlled systems are called indirectly controlled variable. So this was the controlled variable that came from the controlled system, and this will be called the indirectly controlled variable. Okay, and this is represented with Q. Again, this is a very standard terminology. My point is, you need to know all the standard names. All right. So that is what your control system is. So this is the standard control system topology, rather a standard representation of control systems. So in any control system, I mean, these are the portions that we actually really talk about. And of course, every single block that I have here, like the control elements itself, the control systems themselves, the reference conditioning, okay, hold on. The reference conditioning input, this is called P. This is called the reference conditioning system. This is represented with P, right? So all these parts, okay, they can also be subdivided into subsystems. They have certain subsystems within them, right? Is that understood? So again, I just have given you all the particular names of different things, okay, and the mathematical description of different things. All right. All right. Now, very important here. So whatever we are showing with these different inks, like these blue ones, these ones, these are all signals, right? But also, along with any control system, we need to have a mechanism to feed power to the system, right? So you would have a system that gives power to the system, right? So you would have to have a mechanism to feed power to the system. So practically, you would have a mechanism to feed power to the system. Let me just hold on. So the oh, someone is saying noise. Someone is saying, can we consider noise to be a subset of disturbance? Disturbance? No, actually, no. You cannot. Disturbance is a completely different term, and the difference is in how we model it. Okay, disturbances have deterministic mathematical models. Okay, all right. Disturbances usually have. Okay, the question is, can we consider noise to be a subset of disturbance? The answer is no, absolutely not. Okay, because disturbance, because how they are mathematically modeled are quite different, right? Disturbances are mathematically modeled in a deterministic way, right? Deterministic way. What I mean by that is, if we can model the disturbances, we kind of would know the reasons behind the disturbances. Okay, we would be able to figure out how the disturbance would probably change. For example, okay, if my car actually falls into a pothole, what changes could happen? We would be able to model that in a deterministic way. But unfortunately for the noise would be random signals that get added up with our sensors and measuring equipments. So under that scenario, how disturbances and noises are modeled is quite different. And by that definition, disturbance and noise are two completely separate things which do not have, of course, which would have certain correlation between them, but no, you cannot call noise to be a disturbance or disturbance to be a noise. They are two completely different things, because mostly because of their behavior, right? Try to understand, disturbance is not undesired. Try to understand, disturbance is not undesired, because unless you have disturbance, you won't need a control system, right? Everything would be ideal. So disturbance is in the very nature, right, that nothing is ideal. So disturbance is not undesired, but disturbance is there by the very nature that nothing is ideal. But noise itself is not desired. Noise is a very undesired thing. You try your best to eliminate noise, okay, but you don't try your best to eliminate disturbances. Rather, you try your best through the control mechanisms to cater towards the disturbances that you have, right? Do you understand what I'm saying? You need to have a driver because the road is not ideal, the vehicle is not ideal, and because none of those things are ideal. Because of that, you want to have a driver that can cater to the disturbances, that can cater to the non-idealness of the situation, right? But for noise, as far as noise is concerned, okay, you don't want your speedometer to read wrong things, right? Would you want your speedometer to read wrong things, right? When you are traveling at 80 km per hour, would you want your speedometer to read 90 km per hour? No, you won't want that. You would never need that, never want that. And simply because of that, noise is undesired, very undesirable. You try your best to eliminate noise, but you don't try your best to eliminate disturbance, because that is in the very nature of our nature, right? So we try our best to cater the disturbances and eliminate the noise. So disturbance and noise are two very different things, both how they are mathematically modeled and whether or not we want them to be there. We want to eliminate noise, but disturbance, we cannot eliminate them, because if we could eliminate disturbance, it would mean that we are living in a perfect ideal world, which we don't ever, right? So we try our best through our control mechanisms to cater to the disturbances and remove the noise. Understood, right? Again, good question, very good question. As I said, raison d'etre, right? Disturbances are raison d'etre for the control circuit. The control circuits do exist because there is disturbance. If everything was ideal, the control system would not exist at all. Right? So the power system actually feeds everything. So we would have a power system that would actually, and now forget human beings here, right? The power system would feed power into the control elements. The power system would feed power to the controlled system itself. The power system would feed power to the, for example, in a vehicle, you would have batteries, you would have engine, right? Everything, all those power system, it would have feed power to the reference conditioning circuit. It would also feed power to the, how would I show? It would also feed power to the feedback circuit as well. So the power circuit actually feeds power to everything. Okay, and the power system would have different power levels, like an auxiliary power level, like a main power level, and everything. But the point is, everything is additionally fed with power, right? But for our control system classes, we will not talk about power, because those are actually for our electrical engineering domain. Those are taught in your power electronics classes, right? Anyway, so again, if you have any query, feel free to ask. So that's a comprehensive introduction to control system engineering, why we need control systems in any practical situation. And okay, here is the name of the book. I say name of the book, and this is pretty much the standard book. You should not be reading any other book. This is the only book you should refer to. This is Modern Control Engineering. This is the de facto standard book by Katsuhiko Ogata. He's a professor of mechanical engineering in University of Minnesota, and this is pretty much the standard. Someone is asking if there is any signal loss, then what happens to the system? Okay, someone is asking if any of the signal is lost. Okay, so what happens to the system? So question is, someone is asking if any of the signals in any one of these is lost, what happens? Then we have a catastrophic failure. For example, if somehow there is a breakage in this, if somehow this one breaks, then we have a catastrophic failure, because the manipulated variable is no longer being received by the control system, right? So you would probably have fail safes, right? If something goes wrong, you probably want your vehicle to stop rather than go ahead with full speed, right? If something goes wrong, you want your vehicle to stop probably instead of going in full speed, right? So you would probably have a fail safe in order to cater to those situations where something fails. For example, if any of the systems actually fail, you want your vehicle to stop because your life is more precious than your vehicle, right? Something like that. But yes, If any of the signals are failing here, you have a failure. The entire system fails, right? But imagine an aeroplane, for example, right? You are in the middle of the sky, and if some of the parts actually fail, what would happen? I mean, can you just stop an aeroplane right in the middle of the sky? You cannot, right? It's not like a typical vehicle, right? Right? So for those systems, you would have redundancies. Okay, in an aeroplane, you would have multiple sensors doing the same thing. So these feedback elements are redundant. So if a set of feedback elements, so basically a set of sensors actually fail. So for example, and this happened really. Let me tell you a story. For example, back in do you know how speed is measured in flight? For example, how instantaneous speed is measured? Okay, through something called pitot tubes, for example. So you have pitot tubes, and when the flight is moving, like what happens? Through small tubes, air flows, right? And by measuring how fast air is flowing, what you can do, you can measure the instantaneous speed of aeroplanes, right? So one airplane was actually moving on top of North Atlantic Ocean. Maybe I'm not entirely sure. Okay, and what happened? It was winter, and all the pitot tubes actually froze. What happened? The diameter of the inner diameter of the pitot tubes actually became smaller, and because of that, the flow rate reduced, and the meters were actually reading less speed compared to actually how fast the plane was moving. Maybe the plane was moving at 600 kilometer per hour, but the pitot tube was only reading like 300 kilometer per hour. Okay, and that is how a plane crashed. Okay, and I mean, this is one of the life lessons engineers do get by killing people, literally. Okay, so nowadays we have mechanisms to rather redundant mechanisms through which we measure things, through which we control things. If one of the controllers in an aeroplane fails, we would have fail-safe mechanisms that can take over so that a catastrophe does not take place, right? So that you don't die simply. The passengers don't die. But still, accidents do happen, right? There are things you cannot keep in redundancy. But most of the things in those kind of safety critical systems are kept in redundancy, right? All right. So redundancy has this kind of way. For example, for measuring sensors, you would measure the speed by means of different mechanisms. Like you would have INS, means inertial navigation system. You would have GPS, and you would have those pitot tubes based measurement systems, right? And multiple of those. And say for example, your INS and GPS and pitot tube based speed measurement system, they are all agreeing that you are traveling at a certain speed. Then you can rest assured that you are actually traveling at that same speed, because all three different systems that are completely different in nature but designed to measure the speed are measuring the same speed. Okay, are reading the same value, giving you the same value. You can rest assured that your plane is actually traveling at the same speed, right? But if one of those sensors fail and give you a different value than the other two, you would probably know something is going wrong. You would be cautious immediately. So that's how redundancies work. So different people, or rather different sensors, different equipments would do things slightly differently. But if they give you the same result, you can rest assured that things are working fine. So those kind of redundancies do exist in real life, right? Very simple. Many of us have multiple computers. Why? Because if one of my computers fail, for example, if I'm currently doing this on a laptop, for example, if the laptop fails, I have a backup computer. Otherwise, if I just had one laptop, if the laptop fails, I would probably not be able to take your classes simply, right? So yeah, having backups is a good thing, right? Under these kind of scenarios, not in every scenario. Anyway, so that's your answer, I think. Again, ask any question that you might have. And again, this is the book. Please follow this one and nothing else. So this is the standard book. I mean, the most followed book in control system engineering, UG control system engineering. So if you have any question, feel free to ask. Okay, do you have any question, any more question? Otherwise, we will end our discussion here. Thank you very much for being here. And again, if you have any question later on, feel free to ask. I shall definitely be answering your queries. Right. So the name of today's topic was topology and nomenclature of control systems, right? So this is the control system topology, in which we actually draw how things interact with each other, and nomenclature is the names of different things. Okay, someone is asking why human mind is not a system. Okay, I think this actually is a reference to one of our questions back in the last semester. So a system per se is defined, how should I say? Yeah, say it. Okay, there are two properties of a thing that it needs to satisfy in order to qualify as a system. A system needs to have a well-defined physical or logical boundary, and it should be able to interact with qualifying signals, right? And again, what is signal? A signal is a waveform that carries some information, right? So a system should have a well-defined physical or logical boundary, and it should have a well-defined behavior, rather well-defined way in which it interacts with external signals, right? So now talking about human mind is not a system because it probably does not have a well-defined physical or logical boundary. Human brain is a system, but human mind is a psychological term, right? Understandably, so this does not have a physical or logical boundary, okay? And again, it does not have a well-defined behavior, okay, to qualifying input signals, right? If I say you something now, you would behave differently. Maybe you would behave in a way, for example, and if I say the same thing to you, maybe 2 days later, you might behave differently, right? So yes, your mind behaves differently to the same inputs. That way, you don't have a well-defined behavior to external inputs, and right, giving the same input might not produce the same result, for example, and no one can ensure that really. And also, you don't have the boundary. Yeah, human mind is not human brain. Okay, human brain is a very well-defined thing. Okay, it is indeed a system. Human mind is not. Okay, this is an abstract idea. Human mind is an abstract idea. Anyway, funny question. So yes, I don't think any question is there. So if you have any question regarding to what we have studied today, feel free to ask. All right, so if everything is fine, we are going to end our discussion today. I see you tomorrow with Python programming classes, right? Tomorrow evening. All right, so thank you very much for being here. If you have any query, feel free to drop me an email. Thank you. All right.